recognize seeing a graph? What are its basic properties? Is it directed? Is it undirected? Is it simple? Is it weighted? Okay? These are important questions. Okay? We've seen how you can model things as graphs. You should be constantly on the lookout for things that are, somehow can be naturally modeled as graphs, because there is insight in that. Anybody come up with another favorite graph last time? Or, I don't know, maybe pushing it. Anybody over the last, yes? Telephone holes? Poles, okay? So telephone networks, certainly computer networks and things like that are graphs. What are the networks in a computer? Computer networks, that's a graph? Well, presumably the points where, I would say, routers in a physical network are, is, those sort of router things, okay, are vertices. And pairs of wires between router things are edges in a graph. Does everybody make that clear? Actually, the graph we didn't talk about yesterday that is the biggest and most interesting graph in the world is the web, the World Wide Web. What are the vertices in the World Wide Web? What? Not computers. The Wide Web is not on computers, okay? It's web pages, right? What is Google? Google is something that reads web pages, right? What does Google do? It stores the vertices are the web pages. What are the edges in the web graph? Links. Is the web graph a directed graph or an undirected graph? Undirected or directed? Let's think about it. If the vertices are web pages, are the edges undirected or directed? Directed. Okay? You can go from, let's think about it. From Skiena's page, you can go to Skiena's things, right? Or I can go to Yahoo, but Yahoo doesn't go to me directly, right? There's no, so somehow there's definitely a sense that when you crawl a link, you go in one direction on that link, right? I had a link from my page to another page, right? So Google is web pages are a directed graph. What other things is it? Is it a weighted graph? Okay. Is it a weighted graph or an unweighted graph? What are the weights if it's weighted? What do they represent? Could be. Okay. Yeah. Depends upon the search engine. I see. So a search engine might say, Skiena's web page, very important page, right? Okay, your web page, not so important. That's a PageRank algorithm, right? So if you view it like that, it is a weighted, except that's a vertex-weighted one, right? If you think about it, it's a weighted graph where the weights lie on the vertices. They don't tend to lie on the edges so much. Does everybody agree with that? Usually when we talk about weighted graphs, we'll be talking about the weights on the edges. That's not the case here. That's a good example of a vertex-weighted graph. Does everybody agree with that? Is the web page graph a simple graph or not? Let's think about it. Is it simple? Are there self-loops in the web graph? Do pages point to themselves? Yes, I've seen pages point to themselves, right? Are there multiple edges? Does the same page point to another page twice? Yes, it seems to me it is. It's not such a simple graph, right? So it's a good example of, we've decided that it is a directed, possibly vertex-weighted graph, which is not a simple graph. Does everybody see that? Okay. So this is the kind of thing that you should be thinking about when you see graphs. When you see a graph walking down the street, what does it look like? What properties does it have? Okay, and it's interesting to think about. Any questions? Any other properties we talked about these things? I had a bunch on my slides, but we didn't really talk about them. Yeah. Sparse or dense? Is the web graph sparse or dense? That's a good question. Okay. Is it sparse or dense? Who here says sparse? Who here says dense? Okay, more dense than sparse. Do I believe that? Dense means that every web page is connected to every other web page. Do we believe that? How many links come out of my web page? Okay, there's something like, how many billion pages are there to Google indices? 6 billion? Do I have 5 billion links out of each web page? No. The web page graph is a good example of a sparse graph. Does everybody agree with that? The sparse has to do with the number of edges in the graph. If we view an edge as being a direct link, then it is a sparse graph. Does everybody agree with it? How many pages is the average web page linked to? Someone want to make a guess? You say 50, you say 2. My guess is it's between that, okay? Either way, is it sparse or dense? Sparse. Does everybody agree with that? Now, if we wanted to say, so realize that somehow there's a sense that you can get from one page to another by walking through lots and lots of edges. That's not what we mean by dense. We mean that the basic data structure is that it is sparse, few edges, right? And it is clear that the relatively few, it is large. There's a lot of vertices. The number of edges is large in an absolute sense, but not in a relative sense to the number of vertices. That's why it's sparse. Any questions? That's a good point. Any questions? Okay, so that is what a graph is. Now what do you do with a graph? Okay, this is an algorithms course. We're going to want to be able to figure out what data structure should we use to store up a graph. Okay, there are two main data structure ideas for representing graphs. The simplest one is, in some sense simplest one, is the adjacency matrix. If we have a graph on 4 vertices, we could represent all the edges by a 4 by 4 matrix, where edge ij, where the ijth element is going to be 1, let's say, or true, if there is an edge from I to j, and false or 0 otherwise. Okay? We get the idea of what the basic representation is? Do I have a picture of this? I think I have a picture of this. Okay, I shouldn't even have a picture of it. So let's go back here again. We could represent a graph by a matrix where the ijth m sub ij is equal to true if and only if ij is an edge in the graph. Okay? That's what that's saying. Okay? Any questions about that? If I have an n-vertex graph with m edges, how much space does this take up? By n. Does everybody see that? What if I have 0 edges and n vertices? It's an empty graph. Okay? You know, the friendship graph defined among a bunch of hermits. Okay? How much representation memory will it take? N squared. Does everybody see that, even though there's no edges in the graph? Okay? Is this a good data structure or a bad data structure for representing a graph? The answer is it depends. That's usually the right answer to most of these questions. Okay? Let's say you think we could do well with representing a graph in an adjacency matrix. What would be good? What kind of things can we do well with that? If you have a lot of edges, what's the maximum number of edges you can have in a graph on n vertices? N squared. If you have a dense graph, okay, what's the smallest amount of memory you could hope to use to represent a dense graph? N squared, right? If you've got order n squared edges, you have to do something to say, hey, this is an edge, right? So for a dense graph, an adjacency matrix doesn't take up too much memory. Does everybody see that? What can you do quickly with a matrix? Okay, what kind of question could you answer quickly in a matrix data structure? Yeah. Is there an edge between I and j? Okay, are Bill and Hillary friends? That can be answered in constant time, right? Find where's Bill, where's Hillary? True. Okay. Any questions about, or is Hillary and Obama friends? Apparently now false. Okay? Any questions about that? Okay? Fair enough. Now, is there a way we could save space if the graph was symmetric? What is the matrix going to look like if we have an adjacency matrix going to look like if we have a, not a symmetric graph, an unweighted, an undirected graph? Yeah? Do people see that if we have an undirected graph, what does undirected graph means? It means that edge ij implies ji, right? If and only if type of thing. So in some sense, half the matrix is predictable given the other half. Do you sort of see that? If we're given the upper diagonal or the lower diagonal, we get as much information as the entire matrix. So how much memory could we save if we're willing to store it as a triangular matrix? Half. Is that a good thing or a bad thing? Depends. That's the right answer, okay? Why is it good? It saves less memory. What would be less convenient about it? Why would we not, might we not want to store it as a triangular matrix, yeah? Oh, you're saying, well, if I want to find out if Bill and Hillary are an edge. Well, the fact that I have to swap numbers, that doesn't frighten me very much. Why is it? Because somehow, if you think about it, we've assigned each vertex implicitly a number from 1 to n. Right? Bill's number, let's say, is, what's Bill's number? Okay, let's say he was, I think, the 45th president. Okay, and Hillary, let's say she's 007. Okay, that would be her number. Okay? To look her up, look them up, it'd be pretty simple to compare these two. One comparison, which is a bigger number, 7 or 45? The answer is 7 is a smaller number, right? So we would know where to look, right? Does everybody agree? So it's not so hard for me to figure out which indices to look, which pair to look up. Since does everybody see that it's more convenient to represent vertices by the number of the vertex? This is an important point. Than by the name of the vertices, right? We should have some kind of a data structure that for each name, maybe a hash table or something like that, maps each first name to the vertex number, right? And in general, we're going to be using the vertex number. Okay? Any questions? So what's inconvenient about the triangular matrix? Yes? Okay, you're saying that if I can't change it to a directed graph, as time goes by, let's say I suddenly decide that people can be, friendship has deteriorated to the point of view, that it's no longer the case that if I'm your friend, you're my friend. Maybe, okay, although most cases we assume that's a static thing. The thing that I see as inconvenient, how much time does it take to access element ij in a triangular matrix? It's a little bit trickier, right? How do you actually represent the triangular matrix in memory? What was it? How would you do it? Array of array is probably not right. Well, you could say an array of arrays. Okay? Maybe that's one way to think about it. If so, then what are you going to be to look? Or you could, I don't think of it as being you'd use one long array and calculate the position of element ij. It's a little trickier to do in a triangular matrix. That's the only thing that I think about, okay? Triangular matrix is not a data structure that's a built-in primitive in your programming language. It's a little trickier. But sometimes that factor of 2 is necessary. Yes? It should be, if you do it right, it's still order 1. Let's say if you do it right, it is still going to be order 1. Okay? So I will accept that. Yes? Any questions? Okay? Okay, any questions about adjacency matrices? Okay, a good thing for dense graphs, okay, sometimes. Any questions? The other data structure that I'll tell you right now is usually the right one for graphs is what we would call an adjacency list structure. And I want you to make sure it basically has a couple of different components to it. It consists of, first of all, an n by 1 array. An adjacency list structure is going to be an array of linked lists. Okay? So what are we going to be doing? We're going to ask ourselves, what vertices are adjacent to vertex number 2? How would we figure that out? We cruise the adjacency list. This is a linked list of who it's adjacent to. Oh, it's adjacent to 1. It's adjacent to 5. It's adjacent to 3. It's adjacent to 4. Does everybody see that? Okay. What about vertex 4? Who is vertex 4 adjacent to? Let's go to another pen. That's what you do, right? Vertex 4 is adjacent to 2. Okay. It's adjacent to 5. It's adjacent to 3. Okay. 2, 5, 3. Any questions about that? Okay. So what is interesting about this representation? If we have n vertices, that's usually what we'll have, and m edges. So remember that. I'll use these terms constantly. N is the number of vertices, and m is the number of edges. Why does m stand for the number of edges? Because it does. Okay, that's just the convention people use. Okay? So how much space is this going to take up to represent n vertices and m edges? N plus m. Where is the n? What's linear in the space? What is the space that is linear in the number of vertices? Which part of it? This array part here, right? That's an n element array. And now for each edge in the graph, let's say it's an unweighted graph, an undirected graph. How much space? What are we going to use to represent that particular edge? Undirected edge ij. How are we going to represent it? It's going to be 2 of these linked nodes, right? 1, 3 is there. 3, well, it doesn't look like it's here anymore, right? 3. Oh, 1 should be connected to 2 and 5. That's the reason. 1 is connected to 5. 5 is connected to 1. Does everybody see that there's a total of 2 linked list nodes dedicated to each edge? So the total amount of space is n plus, in some sense, 2m times the size of a linked list node, right? And this would be n times the size of a pointer. A pointer is, let's say, 4 bytes or something like that. A linked list node, maybe it's 8 bytes, 16 bytes, who knows? Okay? But linear in the number of vertices and the number of edges. Any questions? Okay? How would we find the degree of a vertex in a linked list? Yeah? Does everybody agree to find out the degree of it? What I'm going to be doing is bopping through the linked list, linked list, and counting how long it is till I hit the nil pointer, right? So how much time does it take to find the degree of a vertex? Okay? You could say it's order n, because in the worst case the degree is order n. But a more accurate way of saying that, it's order d, if d is the degree of the vertex, right? If it's a small degree vertex, it will take little time, right? And if it's a high degree vertex, it will take high time. Does everybody agree with that? So to search for a degree, the degree of a vertex takes order d. How much time does it take to figure out if edge ij is in the graph? How much time? If we have an adjacency list representation, how do we find out whether ij is in the graph? Yeah. How much time does it take? Order d. How do we find out if edge ij is in the graph? We go to the list for edge I and said, hey, are you j? Are you j? Are you j? And if we linked list edge ij isn't there. Does everybody agree with that? Any questions about that? Okay. Yes, question. We ignored the time to find I. If we're looking for ij, Well, finding I, you mean finding the ith linked list? Well, since this is an array of linked lists, how much time does it take to find the ith linked list? The answer is 1, right? We didn't ignore it, or it was dominated. 1 plus the degree. What's 1 plus d? D, okay? Done. Any questions? Okay? Any questions? Okay, good. Okay. So what are the trade-offs between adjacency lists and matrices? Sometimes adjacency matrices are good things. Sometimes adjacency lists are good things. Okay? Which is faster to, like, it's funny, I have this screen here that shows me what it is. I want to cover up the right side here. But putting my hand over it doesn't seem to affect you guys, right? Okay? But which is faster to test if edge ij, a particular edge occurs? An adjacency matrix or an adjacency list? Matrix. Why? It's constant time versus order D, right? So 1 for the matrix. Which is faster to find the degree? How much time does it take to find how many edges are adjacent to a particular vertex in an adjacency matrix? How would we find out whether a particular the degree of a particular vertex in an adjacency matrix? Well, I hear n squared. Let's make sure we're talking about the right problem. Here is an adjacency matrix. Here is the ith row. I want to find out how many edges are adjacent to I. How would I go about doing that? Yes? I cruise through this. Are you here? Are you true? If you're true, yes, I pop up the degree, right? That means that edge 1 is adjacent to I. If not, vertex 1 is adjacent to I. If not, I go to the second element. Are you adjacent to I? Meaning, are you true? Are you true? Are you true? Are you true? In order n time, I could find out the degree, okay, of a vertex, okay, in an adjacency matrix. Does everybody see that? It may be that none of these elements are true, okay? This element has no outgoing edges. But the only way you could find out is by bobbing through all n of those elements. Any questions? Which one uses less memory on what I will call sparse graphs? Okay? Adjacency lists. Does everybody see that? An adjacency list will use n plus m time, space. A matrix will use n squared space. Okay? Big win on a sparse graph. Any questions here? What if we have a dense graph? Okay? And a dense graph, which uses less space? A matrix or an adjacency list? Asymptotically, they both use n squared space. Does everybody agree with that? If you have n squared edges, this uses n plus n squared is the adjacency lists. N squared is the adjacency matrix. There's a slight win for matrices if the graph is dense. Where is the space win come on? For adjacency matrices, yes. Because of linked list versus array, you've got all this pointer baggage that you're carrying around, right? And so you're paying this price for storing pointers. That's where you would lose. Is it a big deal? Well, if your matrix is very, very big, maybe it makes a difference, right? Any questions? Which is faster to insert or delete an edge? Okay, let's think about it. How would we insert an edge into an adjacency matrix? We'll go to the ijth element, boom, turn it into a true, right? How do we delete an edge from an adjacency matrix? Go to the ijth element, boom, you're false, right? How do we insert edge ij into an adjacency list? Yeah? So one thing you could say is if I have an adjacency list, okay, I could just sort of insert it at the head of my adjacency list. Does everybody agree with that? So that would be what? Okay? That would be constant time, provided I'm sure the edge is already not there, right? If I had to actually check to see that the edge was already there, that's more expensive. But we agree that insertion into a list Could take constant time, right? If I didn't do that. How much time would it take to delete an edge from a graph? Order degree, actually it's a little bit tricky here. It has to do with if you have an edge, let's say the edge goes from a vertex of low degree to a vertex of high degree, right? Now, if I'm going to be storing it as an adjacent list, edge ij is going to exist on how many different lists? 2. Does everybody see that? So in fact, I potentially have to cruise down both linked lists. Does everybody see that? Because I have to delete both copies of it if it's an undirected graph. Everybody agree with that? If this bothered me, I could have a more complicated edge node data structure where I have a pointer to who my buddy is, right? And if these were doubly linked lists and I had a pointer to who my buddy was, I could blow both of them away, okay? In constant time, once I delete one, identify one of them. Any questions? Whether this is important depends upon your particular application, but we understand that. Any questions about insertion and deletion in these things? Which is faster to visit the entire graph? Suppose I want to look at all the edges in the graph. Could I look at, how much time will it take to look at all the edges in the graph if it's an adjacency list? How can I look at every edge in the graph? How would I do that? You say n times m? So let's think about it. Here's my adjacency list, right? How could I look at every single edge in my adjacency list structure? Someone give me an algorithm. Probably something that goes 4i equals 1 to n, right? Cruise down the ith list. Does everybody agree with that? So how much time would I spend on that? Okay? It's a little bit, certainly I'm going to spend order n time in these lists, in the loop, right? Plus I'm going to visit every edge exactly twice, right? Because each edge is going to be a node on the linked list. I'll cruise over it once. It would take order n plus m time to walk over all the edges in the, in the structure, right? What am I going to do? Start on this list, bop, bop, bop. Go down to the next list, bop, bop, bop. Next list, bop, 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 right? I spend n time going to different lists. I spend a total of 2 times m time cruising down the lists because each edge appears twice. Does everybody agree with that? If I'm going to have 2 times m records here, I'm going to look at each one of them once for a constant time, it's going to be order n plus m. Any questions about that? Like, I don't see why it's n plus m. Would be a good question. Any questions? Okay? Fair enough. Which is better for most problems? Turns out that adjacency lists in general are the more useful representation. Almost all the algorithms we're going to talk about in this section on graph algorithms will be for really designed to run on adjacency lists. Okay? Any questions about that? And what is the big win with the adjacency lists? What's the biggest single thing about this that is the win of the adjacency list? Which is the magic property? Yeah? The size. The less memory on sparse graphs. This is very, very important. Much of the world is a sparse graph. Okay? Let's think about it. Let's think of Manhattan. Okay? Manhattan, big city, right? If we had the road network of Manhattan, let's say we wanted to represent the entire road network of Manhattan, every junction in Manhattan. Here's Manhattan, right? How many avenues wide is Manhattan? About 10. Let's say it's 20, okay? Maybe it's 20. I don't know if it's 10 or 20. It doesn't make any difference, right? How many streets long is Manhattan? 200 or something. That sounds about right to me. 200. There's some weird streets, but let's not worry about them. There are not that many of them, right? How many junctions are there between roads in Manhattan? How many vertices are there in the road network of Manhattan? Okay, about. How many junctions? How many street lights? How many street lights are there in Manhattan? This is the question. Okay? How many? It should be clear it's got to be about 20 times 200 if we believe this, right? Wherever there is two roads meet, there is a street light, right? That is a junction. In the street network of Manhattan, there are about how many vertices? 4,000 vertices. Does everybody agree with that? If we represented the road network of Manhattan as a 4,000 by 4,000 matrix, how big is a 4,000 by 4,000 matrix? Is that big or small? That's big. How much memory is it? Let's say, I don't know how much you have. Let's say we have one byte. How much is this thing? 4,000 by 4,000 is what? 16, 0, 0, 0, 0, 0, 0. Something like 16 megabytes, right? What if we represent it as an adjacency list? What is the average? How many vertices will there be in Manhattan? 4,000, right? And what's the average degree of a vertex in the road network in Manhattan? 4. Does everybody agree that's what? 16,000. Okay? Entries, as opposed to, wait, no. Yeah, wait, 4 times that. That's about 16,000 entries instead of 16 million entries. Does everybody agree with that? You may say, oh, well, this has pointers. This is a little bit bigger. But there's a big O difference here. Does everybody see this? A road Manhattan, a matrix, adjacency matrix of Manhattan is clumsy. An adjacency list of Manhattan is sleek and small and fits on your pocket calculator. Any questions about that? Okay? That is why adjacency lists are a big deal. Okay? Any questions? Because most graphs in the world are somehow sparse. Okay? Any questions? Certainly big graphs are sparse if you're going to do anything with them, right? If the world was a very dense graph, we can't deal with a big dense graph because it's too big. Okay? So that's another reason why it's sparse. Okay? Any questions? Good. So let me just show you in a nuts and bolts way how you build an adjacency list structure. This is not that complicated. You're going to have to do it as one of the home programming, a little programming assignment for the next homework. But it really is not that hard to do things on graphs, and I want to just make this really concrete. It's in the book, my code, but let's just take a look at it. The structure, we've got an array of vertices. Okay, each node, it's an array. I didn't actually list the array thing. Each node, I have, for a particular edge node, what is the adjacent, vertex? What is the weight? I could represent an edge-weighted graph by setting that. What is the next pointer in the list? That is my adjacency list representation. Okay. What is my whole graph representation? My graph representation is here, an array of edges. This is my array of linked lists. Here I happen to have in my graph representation an array of degrees, so I know what the degree of each vertex is. I could find that out by walking, so this is not strictly necessary, but sometimes it's handy, okay? I know how many vertices there are in my graph, how many edges, and I keep a flag if it's directed or not. That's my graph structure. You may or may not need some of these things, but as you can see, it's basic, simple adjacency structure. Any questions? Yes? So what I've got here is, actually, this is supposed to say I've got an array of pointers, okay? So the way to read this in C is, Edge node is a pointer. Edge node star is a pointer to an edge node. That's what I had on the previous slide. This says, give me an array. Max V is the largest number of vertices that I might have, right? In this case, from my previous example here, going back to it, I said max V was 100. I'm saying I can't have more than 100. I can't have more than 100 vertices. Okay? Think about what this means. It's a good question. This edge node thing, this is an array of pointers. Right? Does everybody see it? There's 100 values. This says I can accommodate 100 vertices because it's an array of 100 linked lists. This says linked list. Okay? Any questions? Okay, any questions about this basic structure? How do I initialize my graph structure? Well, in this case, it's pretty easy. Okay, the number of vertices is 0. The number of edges is 0. I'm accepting a flag. Is my graph directed or not? That I'm accepting as an argument. Okay. The degree of each vertex is 0. Vertex I points to null because there is no edges associated with vertex I right now, right? We have our empty graph. Any questions? How do I read a graph? Okay. Typically a graph representation, you have to read it in from a file, right? How might you store a graph in a file? Okay. A common way to do it might be to say, well, here's vertex 1 is adjacent to 3, vertex 1 is adjacent to 5, 2 is adjacent to 3, 3 is adjacent to 1, 3 is adjacent, well, it depends if I want to say is it directed or undirected, right? If I'm using an undirected graph, I probably wouldn't list both of them, right? If I know it's an undirected graph when I'm reading it, right? The question of when I read it, do I know whether I mean a directed graph or an undirected graph? When I read it, I'd better know, right? That's why I'm letting that be a flag that's being passed to me. What am I doing? I am reading the number of vertices and the number of edges. This has 5 vertices and 7 edges. Then I have a loop. For I goes to the number of edges. Read the 2 vertices on that edge. Then I call a routine, insert vertex I, the vertex xy, the edge xy into the graph, assuming we know that it's directed, whether it's directed or undirected. The hard work is done by insert edge. What does insert edge do? It starts out by allocating space. If you're a C person, you worry about that. If you're a Java person, maybe you didn't worry about that because it was garbage collection. It allocates the node for me to add that element to the link. In this case, it's an unweighted graph, so the weight is nothing. Okay? This new edge, if I'm inserting edge xy, I set the second field to be y. That's what the destination edge is. I link this new node into the edges here at the front, right before I had, Here I had before, this is the X list. It pointed to a linked list of things, right? What am I going to be doing? P.next is going to be equal to the first element on the X list. That's what this is, right? The first element on X linked list is now assigned to point to Y. Now this element is in the linked list, right? I bop up the degree. If the graph I was supposed to insert if it was a directed graph, okay, I may or may not have to insert copy X and Y. And this is basically governing that, whether I insert another copy to it. If I read an edge ij in a directed graph, I don't insert edge ji, right? People see what I mean by that? If, on the other hand, it's an undirected graph, I've then got to go insert it in the other place. Any questions? Okay, yes. Well, that's bull. No. The answer is that I defined my own bool type. Okay, I set up my own structure. Okay, bool, which is 0 or 1, the way it's supposed to be in C. Okay. Any questions? Okay. Any questions? Okay. Let's keep moving here. What's this thing here? Sorry. And I think that's the edge of basically. So from this thing, I now can insert a graph, an edge into the graph, and build my graph that way. Any questions about how you build one of these adjacency lists? It is not all that complicated, right? Any questions about it? Okay. Now let's go to the next lecture. Lecture 11. Okay. And then let's come back here. View. Okay. Boom. Okay. So I asked you for the problem of the day. Had to do with converting between data structures. Let's think about this now, because again, there's complicated things we're going to be doing on graphs and simple things we're going to do on graphs, right? In general, the simple things are more important. If you can't do simple things, you can't do complicated things, right? The basic data structure manipulations of how do you store a graph, how do you read it, how do you write it. You can't do that, you can't play the game at all, right? That's why this is fairly elementary. I want to make sure people get it. Question is this. Suppose I give you an adjacency matrix, and I want you to convert a graph in adjacency matrix format into a graph in adjacency list format. How would you do it? Okay? Can someone give me an algorithm to convert an n by n matrix in adjacency list matrix format into an adjacency list representation of that graph? How would you do it? What would the algorithm look like? Okay, I've got two people who can't hear you. So you say what? The basic thing is going to go something like 4i equals 1 to n. 4j equals 1 to n, right? If m sub ij is equal to true, what am I going to do? Insert edge xy into the adjacency list, right? We just saw how to do that, right? Does everybody agree this is basically the algorithm? What is the running time of this algorithm? N squared. Does the number of edges in this algorithm matter? No. Does everybody see that? This is an order n squared algorithm. And I get the adjacency list structure out of it. Any questions about that? Okay. Very good. What if I wanted to go back the other way? Let's just think about that for a second. Now let's suppose I want to go from an adjacency list to an adjacency matrix. How would I go about doing that? Okay. Here I've got a nice adjacency list. And I want to build an adjacency matrix for it. What would I do? Yes. Well, let's think what I would be doing. First of all, I'd probably say 4i equals 1 to n. 4j equals 1 to n. M sub ij, I'd probably initially say is equal to 0. Right? Or false. I'd initialize the graph to being empty. Does everybody agree with that? That's probably my first move. Right? Now I've got a completely empty matrix. Now what would I do? Okay. What would my next move be? The ijth element of what? I want to try to fill in this thing, but how do I find this thing? I want to now go from an adjacency list to an adjacency matrix. How do I fill in the adjacency matrix properly? What is my algorithm here? Okay, question, answer, yes. goes 4I equals 1 to n, while not nil. Right? Now I'm going to cruise through the ith list. Did everybody see that? I'm then going to say m sub I, what, p points to dot y is equal to true. Does everybody see that? That's my basic metaphor here. Okay? I'm going to go through and loop through all the lists, and for each list, go through all the elements and set that element to be true. Does everybody see that? Questions of how that works. How much time does it take? I hear what? I hear something that says it's order n squared plus what's this? nd. I like to say n times d is n plus m. Okay? I like to partition out the number of vertices and the number, because what does n times d mean? Are all the vertices of the same degree in a graph? Let's think about the friendship graph, right? Somebody has a lot of friends, and somebody has very few friends, right? What's d? Okay? You may say d is average, right? But n times d average is m. Okay? Any questions about that? Okay? Any questions at all about this? So this would be n plus m plus n squared. What's the combined complexity? N squared. This is bigger than that, because m is always less than or equal to n squared on any interesting graph, or any simple graph. Any questions? Okay. Let's look at one more of these. Okay? There's a special type of graph structure that's sometimes interesting, although for your purposes probably not so, called an incidence matrix. What is an incidence matrix? It's a matrix that is n by m. There is a column for each edge, right? And there's going to be an entry, okay, m sub I, j, if edge vertex I is incident on edge m, j. What does that mean? Let's say we had an array of edges. Here, it's an array of two-element things, right? Edge 1, 3, 1, 4, 2, 3, 2, 5, 3, 6. Here we've got 1, 2, 3, 4, 5 edges in our graph. Does everybody see that? We could imagine a structure here where what we want to do is, we had it here. 1, 2, 3, 4, 5 edges. And they were on 6 vertices. So what is this? 6 vertices. 1, 2, 3, 4, 5, 6. 5 edges. Right? And we want to now know, is vertex I, let's say this is 1, 3, is vertex 1, 4, is vertex 3 incident upon edge 3? The answer is no, right? Because edge 3 consists of 1 and 4. That's what we mean by an incidence matrix. Do people get the idea that we assign a number to each edge and a number to each vertex? How many trues will there be in any column of this matrix? I see 2. Why 2? Because each edge is incident upon exactly 2 vertices. Does everybody agree with that? An edge goes from one vertex to the other. How many trues will there be in the row for vertex I in this incidence matrix? 1? No. Yeah? It's degree, right? Does everybody see with that? A vertex is incident upon a certain number of edges. Any questions? So how could we build this incidence matrix? How much time do you think it's going to take? Okay? How big is this incidence matrix? It's going to be n times m. Does everybody see that? We'd probably, again, same basic structure. We initialize it all to zeros. We then loop through the edge list of edges and set the appropriate bits to be true. Okay? Any questions about that? Any questions how you manipulate these kind of data structures? Okay? Any questions? Okay. So, it's taking a little longer than I wanted, but let's now talk about the first, what I'll call, interesting problem on graphs. Okay? We now know how to represent the graph. What is the best way to represent the graph? Adjacency lists, right? One of the biggest problems that comes up as sort of a building block for real graph algorithms is the question of how do I walk over the graph? Okay? So let's think that I am trapped in a maze. What is a maze? A maze is a bunch of places where I can walk from one place to another along a hall. And at a junction, I have decisions of where I can go next, right? Let's say I am here in my maze, and this is the exit. How can I find my way from here to the exit? Okay? Let's think about it. If I want to get out of this maze, what algorithm do you normally use? Have you ever been in a maze, trapped in one of these big hedge mazes that they sometimes have? They're kind of fun to walk through. Who's ever seen a hedge maze or been in something like that? Okay? How do you get out of a hedge maze? You're trapped in a maze. Yes? So the claim here is that if you're in a hedge maze and you keep your hand on the left wall, right? You walk, here's the maze, right? Here's the exit. You start here and you keep your hand on the left hand on the maze, right? The left wall. Does everybody see that? And you walk around and around and around and around. Does everybody see that in this disconnected maze? Do you see what disconnected maze I mean? This is part of the hedge. This is part of the hedge. This is part of the hedge. Here is the maze. You have this idea that if I walk, let's say I want to get out of this room, right? There's the exit. All I have to do is to keep my right hand along the wall. And if I keep walking all the way around and keep my hand on the wall, I will get out of this maze. Is that right? Or am I going to get trapped? It has to do with the question of, well, what's it mean by connected? Let's think about it. Okay? There's a sense somehow that this floating island is a weird thing. That's what you're trying to get at, right? But it's a question of, is what connected? There was certainly a way for me to get outside. If the walls were all in one piece, that method might work, okay? And I believe it does. Does everybody see that if the walls are not in one piece, that doesn't do the job? Even though there is a way out of the room, right? People see that? So how do you get out of a maze normally? If you just adopt a thing where I'm always going to make a left or a right turn, there is no way that I guarantee myself getting out, right? Unless maybe you're assuming something about a maze, okay? That doesn't seem to always be true, okay? I could just wander around randomly. Am I necessarily going to get out of the maze by doing that? Well, maybe doesn't mean necessarily, right? Okay? You can wander around randomly, okay? But I don't think you're necessarily getting out. How can you get out of a maze? Guarantee yourself getting out of a maze, okay? This is really the heart of the question at graph traversal, okay? What? Well, try every single path. Now you got to be a little bit careful here. If I do indeed try every single path, that might work. But there might be lots and lots of different paths. That's what you mean by paths. Okay? Every possible sequence of walking steps, there might be an exponential number of them. If a path means some way of weaving in and out among the aisles, right? I could weave in and out of the aisles arbitrarily and not repeat my weaving steps. Okay? It's a question of what you mean by repeat. Yes? Okay, the key thing to getting out of the maze is knowing when I have been someplace before. Everyone remember their Greek mythology about the people who were trapped in mazes? What did they do? Okay, and there's a couple of these different stories, right? What did the person do who was trapped in the Crete, in the Minotaur, right? The monster was going to eat them or something in the maze, right? How did they get out of the maze? Anyone remember? Either you drop breadcrumbs along the way to make sure you know where you've been, or I think maybe they used hair or something like that. I have this image of them writing down, or maybe writing down where you were. The key point is this: to avoid getting trapped around, what I need to do is to get at this podium here and say, okay, I am now at this point in the podium, right? As I go walking around by this right-hand rule, okay, marking every place where I've been, I think I'm making progress now, right? Until I get back to where, oops, I've been here before, right? If I go in this direction, I've already been there, right? To avoid me getting trapped, I've got to say, I can't go there. Where is another place where I can go, right? And if there was a way out, there's got to be someplace back here where there's another path to go in, right? The key idea in graph traversal is to make sure, and again, you'll see the programs and stuff, but somehow there's going to be two issues. For efficiency, to make sure we don't repeat over and over again, we have to make sure we visit each edge at most twice, coming and going. I'm going to do that by marking things. For correctness, we're going to make sure that we visit everything, every vertex in the graph, if there is a way to do it. If there's a way out of the maze, if we systematically visit every point in the maze, we will eventually find it, right? Those are the issues in graph traversal. Any questions? So the key idea here, the thing that makes this work, is that we are going to be marking when we visit vertices and what the status of our visits in there are. Okay? Again, a lot of these ideas in graph algorithms, some may sound simple or stupid, this idea of, yes, you're marking it. The problem of how do you traverse a maze and get out of it is a subtle problem. Okay? It's important you understand how depth first search does it, where other ways of doing the search don't do it, right? So what are we going to do? We're going to take every vertex and actually mark it as being in one of three states. Either it's undiscovered, meaning we haven't seen it yet. Okay, if I'm plopped in the maze, just drop me in the maze someplace. Everything out there is undiscovered, right? There are certain places in the maze that have been discovered, meaning that I know that it exists. Right now, the place where you dropped me in the maze is the only place where I know it exists, right? Then what I'm going to do is, for every place in the maze, there's a certain number of possible directions I can go in. Once I have explored all of these edges, there's nothing left for me to learn from looking at this vertex, right? If I have tried to explore all possible exits from here, and all possible exits from there, and all possible exits from there, and all possible exits from there, and all possible exits from here, there is nothing else I can do and hope to discover something. Does everybody agree with that? So at some point, a vertex is going to be processed, okay, done, finished exploring. Once I have looked at all the outgoing edges from it. Any questions about that? So we can think of graph traversal as being, for every vertex in the graph, an evolution from virgin undiscovered to completely processed and done with. Okay? Any questions about that? Okay? Okay? And again, the order has to go, obviously. We start out, a vertex is undiscovered. First time we walk over an edge to that vertex, we discover it. Once we have explored all the edges going out of it, it is processed. Any questions? So, the data structure for exploring a complicated maze is not just, when you're wandering through a maze in a hedge, you don't really have any data structure, right? You're just lurching around, and you are the data structure somehow. What we need to maintain to make our search work is a list of places that we know we haven't finished exploring yet. Okay? So let's start on a particular graph. Maybe I'll just draw an example here. Here is a graph. Let's say I want to explore. Here's the exit. Here I am. What could I do? Let's say there's vertex 1, 2, 3, 4, and E, right? Originally, I'm at vertex 0. And vertex 0 is all I know about. I haven't finished exploring vertex 0, right? What could I do? I wander down an edge. Now I've discovered vertex 1, right? I'm now going to go look out at vertex 1 and say, where else can I go? Look, I can discover vertex 2. This might be one way I wander. Oh, look from here. I go and discover vertex 3. That's good. I go and discover vertex 0. Now I'm back where I am. What is the next thing I can do? I can go back up and take a look at vertex 3 and say, hey, from vertex 3 I can go discover vertex 4. Right? When I look at vertex 0 here, I might decide, wait a second, I've looked at all the outgoing edges from vertex 0, right? So vertex 0 is now not so interesting anymore, right? Vertex 3 is, oh, look, I discovered vertex 3. Vertex 4, that's good. From vertex 4, maybe I'll now wander to vertex 2. Okay? From vertex 2, now, oh, look, I discovered vertex here. Do you see that I need to keep track of where have I discovered and not yet completely finished with, if I'm going to guarantee that I eventually get to everything? Any question? That's the idea of the to-do list. Okay? Any questions? So basically the idea here is if I keep track of all the places that I've been and make sure I explore everything that is on every place where I've been, eventually I will visit everything that is reachable. And I will know when I have finished reaching everything that is reachable. Okay? When I've looked at every vertex, I've looked at all the outgoing edges. Then there's no place else for me to go. Does everybody agree with that? And that sort of be the argument that, in fact, I will eventually visit everything that there is to be visited. Any questions? So, what turns out to be, any question about how the basic idea of how you do a traversal? Now, when you're wandering through a maze, you're doing it in a kind of a lurching way. It's unpredictable what you're doing. It turns out that doing it systematically, doing the exploration of your to-do list in a systematic way, makes a difference in what you can do with your traversal. The algorithm known as breadth-first search, okay, visits the vertices in the way that we explore them in their distance from our starting point. So if we want to explore the world around this vertex, we're first going to explore all the vertices that are adjacent to it. And then we're going to explore all the vertices that are adjacent to the ones that we have just explored. And then we're going to explore all the ones that are adjacent to that. Does everybody see that this breadth-first search thing is a kind of branching out, a radiating out search from here? We're going to systematically explore beyond this, right? We set fire. Let's say we have a forest here. We set fire to the forest here. Okay, the fire is going to burn down the forest, right? Exploring all the trees as it burns, right? It's going to be doing a breadth-first search. Does everybody agree with that? It's radiating out like that. Okay? Any questions? Now suppose we set fire to one guy, okay, and he's running through the forest, setting fire to the forest, right? What's going to happen? He's going to explore all the trees also, right? But not in a radiating out way, right? He's going to run as far as he can before backing up. That's maybe analogous to depth first search. Don't take that analogy too carefully, okay? But any questions here? The idea here between these traversals is going to be that if we store the list of, okay, so the key idea that's going to separate breadth first search from everything else is going to be the structure in which we store the to-do list. What do we do next? Okay? If we store it in a first in, first out queue, that's going to have the property that the next thing, if it's in a FIFO queue, the next thing we choose to explore is the thing that's been in the queue the longest, right? That was the thing that got discovered the longest amount of time ago. So think about it. Suppose, let's say, we go look at here. Oh, look, I discovered somebody, discovered somebody, discovered somebody. Who is the oldest? Now I've looked at all my outgoing edges. Which vertex is the oldest now? This one, right? The one that got inserted in the queue first. Well, now look at the outgoing edges from that, right? And every time we discover somebody new, it goes into the queue. But the next thing we explore when we finish it is the oldest one. If we do that, the search is going to naturally radiate out from the point of discovery. Any questions about that? Okay? Fair enough. So let me show you a program for doing breadth first search. Okay? And we've got a few minutes. I want you to try to concentrate on this for a second. Because again, this graph traversal thing is not that hard, but it is a little bit subtle. How many people saw breadth first search in a previous class? You all have seen it, right? No problem, right? Now, breadth first search is not that hard, but it is subtle to see exactly why it works, why you don't get trapped, okay? Why it efficiently explores something. There is something subtle going on. Not complicated, but subtle and elegant. What are we going to do? We're going to start out our search by initializing two arrays. I did it in this way by two arrays. I have an array for every vertex processed and discovered. Okay? Originally, every vertex is not discovered and is not processed. Does everybody agree with that? Every vertex is in a virgin state. So I'm going to have flags here. Discovered, false. Processed, false. What is the evolution in the state of the vertex is? When we discover it, it's going to be changed. We discover vertex 2, the discovered thing is going to become true. When we have completely processed it, the processed flag is going to be true. Does everybody see that? These two Boolean flags can let me go through the three states that I want. Okay? Virgin, discovered, completely processed. Any questions? You could probably do it by an enumerated type as well. If you like doing it that way, that's fine. Any questions? So what am I going to be saying here? Okay? That every vertex is neither discovered nor processed, and the parent, which is going to be the discoverer of each vertex, is set to -1. If I haven't been discovered yet, who discovered me? No one, right? I'm undiscovered. So that's what this is initializing to. Any questions about initialization? What is the guts of the breadth first search implementation? Let me walk through this. Again, it's in the book. You should look at it. What am I going to do? I start out with a queue of what vertices, okay, am I going to still have to process, right? Originally, it is empty. When I start my search, I'm going to have to start from some vertex, right? If I start to explore the graph, Suppose I tell you, you tell me, start to explore this graph. And I'll say, okay, where is there a vertex I can start from? I'm not going to tell you where the graph is. Can I start to explore it? This graph could be anywhere on Earth, right? It makes sense that I have to start someplace. So let me start from one vertex. First thing I do is NQ the start vertex onto the Q. What does that mean? It means that vertex is where I'm going to start exploring from. And I set the state of my start vertex to discovered to be true. Yes, I have discovered this vertex. How did I discover it? You told me about it. Okay, that's how I discovered it. Any questions? What is the guts of my loop? While the Q is not empty, meaning that there is still somebody who has been discovered and not finished, right? Is there right now somebody who's been discovered and not finished? Yes, the start. Take that vertex off. You're my first person to explore. I am now going to say, yes, I have processed you. And now I'm going to take a look at all the outgoing edges from this vertex. For each, as I traverse that linked list, I'm going to discover another vertex. Basically, this vertex V is adjacent to Y. Did I discover something walking from V to Y? It depends. What does it depend on? Under what condition traversing edge VY will I discover something? If Y had never been visited before, right? How can I tell? Well, has it been discovered is a test, right? Has it been processed? If it has been processed completely, I'm not going to care at all about it. Okay? Then, in fact, I'm going to do something to the edge potentially. The key issue here is, have I discovered it? If I did not discover it, what am I going to do? I'm going to say Y is now enqueued as a new vertex to be stuck on my Q, right? I have discovered Y. Because V discovered Y, V is the parent of Y, right? And now I have finished exploring it, that edge. I'm going to keep going on through the rest of my vertices. Any questions about that? Look at the basic breadth first search code. Make sure you understand why it works, why it doesn't get trapped, why it does that thing. And we'll talk more about that next class. Any questions? Thanks for your attention.